We are live.
What's going on? We're back. Rob, you there?
What? Who?
Are you You there? Okay, so make sure you're there.
All right, there we go. We got the screen share going, so it looks like we are live and ready to go. And hey guys, what's up? So what are we covering today, Ryan?
Transactions. Coin Guy Bry. You know that.
Coin Guy Bry, sorry.
Kidding. Transactions. I mean, this chapter is broken down into two parts. I thought it was simple from the beginning, because we did learn this in the programming blockchain thing with Jimmy. But it's there's a lot of variations of transactions. You know, there's the Coinbase. There's just your simple one person. There's coin joins. There's with multiple inputs, and then there's like wallet consolidations with. So yeah, it can get evil on you pretty quick. But yeah, what did you think of it?
I think it was pretty interesting. I think once we actually start, doing something, building transactions and testing things out, we'll get a better understanding of it. But I think we'll be able to at least cover transactions and the pieces of them and the majority of what each part of the transaction does and the script that the transaction executes.
So I guess the plan is what to do. Probably not doing much coding today. But the next episode, since it is split into two parts, we'll try to build. We'll try to just build the hex code, generate a transaction on the test net.
Yeah,
and that'll be the next episode.
Yeah, exactly. Yes, let's try to send something out.
This one's a big one to swallow.
Oh yeah.
Yeah. I guess we can get started.
For sure, and I just want to make sure we cover the book. We got Mastering Bitcoin by Andreas Antonopoulos. That's what we're covering here. We're on chapter 6, transactions, and the next chapter will be advanced transactions. So we'll just cover the basic outline of what transactions are and how they're built, and the pieces of them. And definitely check out Andreas's book. Buy it, read it online as well. It's on GitHub as well, and also check out his YouTube channel, Twitter account, all that. Highly recommend.
It's not for the weak. It's not for the book's not for the weak at heart. It's
yeah. Oh, for sure.
So, yeah.
And that's why we're trying to break it down live.
Yeah, so, the Internet of Money, his other book, is actually it's a readable one for anybody.
Not technical at all. I actually just finished it. I listened to the audiobook in my car, and it was awesome. I would highly recommend it.
It talks about more about. I remember him saying that book talks more about the why it's important, and this talks about the how.
Yes.
So
yes.
Anyways, we can get forward going on this.
All right.
So I guess one thing. Oh, you can go ahead.
Oh, go ahead.
So I guess one thing I learned in this chapter is that the blockchain is really just simple. It's just transactions. There's a list of transactions. The wallet, the application. That thing is the workhorse. That thing does a lot to build a transaction. That thing's got to do a lot of work. The blockchain just says, here's some transactions, just boop, 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 boop on these lines. The wallet's got to look over here. It's got to jump up the list. It's got to consolidate. It's got to memorize which ones are unspent. Really, wallets. That's why these wallets are. The apps are probably a lot more in depth than you would imagine. The blockchain is simply QuickBooks.
Yeah, it's the database.
A blockchain, this blockchain stuff is literally just a ledger. It's nothing special.
Yeah, where the wallets are doing the majority of the work, especially for sending and receiving transactions. The wallets have nothing to do with what people would traditionally think would be, holding your coins. No, like we said in the previous episode, your wallets do not hold anything besides your keys, your keychain to access your Bitcoin in the blockchain. But they also do a incredible amount of work scanning the blockchain to build your transactions to send and receive Bitcoin, as well as keep track of your unspent transaction outputs, which we'll cover here shortly, to calculate what your balance is. So
and then get the fee part right. It's got to get, that's a tough one. The fees are really. We'll talk about it later, but it's really left out of the equation, and you don't want to forget about it, and you can forget about it and overpay, and so the fees were kind of interesting to me.
Yeah.
So
yep.
okay.
We actually have some someone chatting with us on our live chat saying hello and saying how there is no Bitcoin, and that is very true. There are no coins. They're the Bitcoin is really just one of those words that helps us relate to it a little easier, but in reality there are no coins. There are just transactions and
just numbers
records. Records of inputs and outputs. Input of X amount, output of X amount.
Here's how rich this guy is. Here's how rich this guy is.
Yeah,
here's
exactly.
how poor this person is. There's no coins involved.
Yeah.
It's a leaderboard. It's a status list. I mean, if you think it that way, but
oh yeah,
that's all it is. It's a leaderboard.
So we're probably going to start a screen share here on my end, and we can kind of discuss. Yeah, exactly.
So I guess we got our first notes here. We talk about transaction. So I guess you want to jump into the website first. Okay, yeah, we'll start at the JSON.
Yeah, we can just start here, just to kind of a launching off point. This is kind of what a transaction can look like. This is one interpretation of a transaction. This is a way that is a little more human readable and friendly to understand what goes into a transaction. So when your wallet software or you as a programmer builds a transaction, you'll need to know, several things. You'll need to know the transaction ID, the identifier of the previous transaction that you're referencing that contains the unspent transaction output. So the best way to put that is that you say that previously you received a value of Bitcoin from someone else in another transaction, and that output of that transaction is actually going to be the new input of your transaction that you're going to then use to send, a value to someone else. So it's kind of like a chain where the blocks are chained together, but the transactions are also chained together because transactions have to refer to a previous transaction in order to really send anything. Go ahead.
It really doesn't look back to a balance. It doesn't look like how much money do I have here. It looks back to, what was the last transaction I did, and okay, that transaction looked back to this transaction. So really a transaction, the first part of it, it looks back to there's no, maybe a wallet holds a balance for you, but how the whole thing works is it's just referencing. The only input information has is the last transaction hash. The transaction ID, transaction hash, the same thing. Which you can search on a block explorer. That's the thing. That's the only chunk of information it takes to look to get all the information it needs. So
exactly. So just a quick way to show it here. For example, say we're looking at a transaction. We're breaking down that transaction into multiple pieces. There's always going to be breaking down. There's always going to be an input. There could be more than one input, but this is basically where the Bitcoin, if you want to call it that, the value is coming from. So it shows input 0 for this transaction is actually pointing at previous transaction 8EC, so on and so forth. So this is actually a transaction that was executed on the blockchain. It could have been yesterday. It could have been years ago. But it references the amount of Bitcoin that you received previously, that you're going to now turn around and send a portion, or if not all of it, to someone else or to another wallet of yours. There's many other circumstances, but you'll always see at least one input. With
I think you gotta spend all of it. I guess you said portion, but
you can spend all of it towards someone else, but you have to
the change then. But
yeah, good point.
Yeah, you always spend your inputs.
Exactly. So to keep it in the simple view, we're looking at a simple transaction that occurred today, October 13th, at 22:10, and the previous transaction that it references is here. the index of the index here is referring to what the index or the number of output that you're referring to in this transaction.
Do you want to show them on Block Explorer?
Well, I can probably show them on here if I open this up.
Oh, you're right.
If I just click on this, this will take me to that previous transaction, and the previous output 0, which this index was referring to, 0.
It's 0 base, so 0 is 1, 1's 2.
Exactly. So that transaction we were just looking at was referring to output 0 as the source, if you want to call it that, of 176 Bitcoin. So if I go back here, you'll see that this transaction was referring to the 176 Bitcoin output in this transaction, and now it's going to send 0.05 of that 176 Bitcoin to someone. This actually may be the change, but more than likely this is probably the amount that someone is using to perform a purchase, for example. They're sending 0.05 Bitcoin to Bob, and then they're sending 176.20 Bitcoin back to themselves.
Yeah. Most likely.
Most likely, but it could be the other way around. Yes, exactly. So I could be sending 176 Bitcoin to Bob and receiving 0.05 as change. Okay, so that's the thing, is there's really no way to tell, because the addresses that you're sending to and your change address can be completely different, as we mentioned in our previous address.
No relation. I mean, except for with the seed there is, but you wouldn't know it.
Exactly. So one of these addresses could be you, or more than likely going to be you. One of these addresses is Bob, but we can't tell really which one. I mean,
you can guess. I mean, that's, I think, a lot of explorers, they try to, there's obvious kind of, I don't know what I'm trying to say, but
there's obvious kind of patterns in spending. Yeah, like my guess here, and probably most people's guess, is you sent 0.05 Bitcoin to buy something, and you just want your 176 Bitcoin back as change. Because you don't want to spend 176 Bitcoin. That's a lot of money.
Well, yeah. I think that was pretty obvious. Yeah.
I think 176 times.
It'll cost 177. How about 176?
Yeah. So roughly $880,000. So if this person is buying a jet, then this is probably what's happening here. But they could just be buying
keep the change.
Exactly. They could just be buying $250 worth of candy.
Yeah. And then I guess we kind of jumped into this site. You want to kind of run through it real quick and kind of show you what it does? This is a really cool awesome site.
Very cool. It's a great tool to learn how the blockchain is constructed and the pieces of it. It's called Blockchain Reader. We'll paste the link in the description below. But basically, if you start here, you start at the main page, you'll get Last Block, Mining Simulator, and Contribute. Mining Simulator is something we'll get into in the mining episode. This is a very cool way to visualize mining and how it works. Whereas Last Block will take you to the most recent block in the blockchain. So when I click on this, it's going to give you the data that's in that block in a nice, friendly, easy to read format. And you can hover over the different pieces to learn about what each piece means.
I guess we need to mention this is in hex, just for anybody that doesn't know what.
Oh yeah,
16 base number systems.
Exactly. All these values here are hexadecimal, and this is the way.
Two hex make a byte.
Exactly. So each one of these represents a byte. C4 is 1 byte. C9 is another byte. So this is actually where the block size comes from and the transaction size comes from. Is this raw hexadecimal is how the data in the block and transaction are
serialized, right? It's how it's sent. It's sent in hex.
Exactly.
Everything, your fees are based on your fees are based on bytes, satoshis per byte.
Yes.
Right. So you could send $1 million and make it just one address, and your fees are real cheap because it's just there's not you're not sending it to 20 different addresses, or you're not pulling from 30 addresses. So
exactly.
Dollars don't matter. It's just the amount of bytes. How much ones and zeros you're sending on a transaction. That's your fee, just based on that.
Yes, exactly. And you'll see this is the actual total size in bytes of the block, which contains all the transaction.
That's
and
the size. Oh, that's the block. Okay.
This is the block size, so 986,000 kilobytes, which is close to a megabyte, which is the current block size limit. Correct.
Yeah,
Yes.
I mean we're not gonna get in the segue.
No, but
one step at a time. Yeah.
But it is the block size limit, so you're always going to see roughly around 1 megabyte, or for now. So now, if we scroll down further, this is just data on the block, which we'll get into in a future episode. We're not covering the actual blocks at this time, but you're going to see what's called the Coinbase transaction, which I think we can probably cover now. So this is actually the first transaction in every block. So this block is actually one of the only, or the only transaction that will have no previous transaction hash. And you'll see this here. All these zeros here are the previous transaction hash, which means it's pointing at nothing. Like there's no previous transaction to this transaction
to refer to, and so
refer to.
This
is actually
prove it.
Exactly. This is actually creating Bitcoin. This is the miner's reward, essentially. So what you're seeing here is when the miner built this block and validated all the transactions, and once they were able to prove that this is a valid block, they created this Coinbase transaction to themselves, basically writing a check to themselves with a value of the block reward, which is currently 12.5 Bitcoins, and also any fees that were calculated from the transaction within the block.
So we got a question real quick.
Okay, go ahead.
I think MTG Cash Cow, he's been on our episode before. MTG Cash Cow, he asked how many hexadecimals are in one transaction? So how many bytes? So there's two hexadecimals in one byte. How many bytes are in one transaction? It depends. I mean, on average, I guess. Do you do the on average?
I believe the on average is of roughly 250 bytes. So
per transaction. It's like me sending it to one person, I get a change back, right?
So you'll have 125 hex values, if you will. Like if each one of these pairs, hex values, pairs 00, for example, were counted as one, it would be 125 roughly, maybe more. It really just depends on the amount of inputs and the amount of outputs that are in the transaction.
Yeah. So if you received a whole bunch of money from different people to one address, like a donation address, and then you want to send it out from that address, that the input side of it is going to be real long. So if you're going to have a bit, this kind of clicked on me. If you're going to transfer money out of your donation address, you're probably going to have a higher fee than you would just a regular brand new address.
Exactly.
Right, Rob? Does that make sense?
No, yeah, that makes sense. I was thinking about that myself. It's because you receive, say, 1,000 donations.
Yeah,
those are 1,000. Those are 1,000. Exactly.
Transaction like that. Yeah.
Yep. That's you got to pull from 1,000 unspent transactions
in order to condense it into one.
To build one transaction with 1,000 inputs to send to just one output, for example. Or two outputs. So yeah, back to the Coinbase transaction. Again, this is basically the transaction that creates Bitcoin. So currently everybody gets 12.5 Bitcoin when not everybody, but the miner gets 12.5 Bitcoin when they successfully mine a block, and plus any additional fees that were incurred in the transactions. So for example, this miner got 13.57 Bitcoin for mining this block. The 12.5 block reward plus the additional equals the 13.57. So this again is the only transaction you'll see with all zeros, because it is not referencing any previous transaction. It is actually where Bitcoin comes from. Is
there any way to go to blockchain.info and then to pull up a block, and it really does, the first transaction, you can see it right there. It doesn't have an input.
Yeah, this would be easier to see. Yeah, if we go to the most previous block on blockchain.info and we scroll down, we'll see that the transactions has no inputs. This is newly generated coins. This is brand new, never seen.
That's where the money is. That's where the printing comes from. Money, Bitcoin printing, right there. And just adding numbers in the ledger.
It was $82,000 that was created plus the transaction.
I wish I had a mining facility. Jeez.
Exactly. So whoever mined this block was rewarded $82,000. That's the 12.5 Bitcoin plus the additional fees that were incurred. So the transaction fees for this block was $11,000. So roughly two Bitcoin.
2,500 transactions looks like.
But yeah, 2,500 transactions that spent. That's what output means. That was spent 80,000, or $80 million. I'm sorry. Wow. Oh my god.
Okay.
Okay. So yeah, it takes a second to realize that this is serious. This is serious money that's
estimated transaction volume.
So yeah, that's the estimated transaction volume is 5 million, where the output total was 80 million. So if you think of it that way, the best way to put this in perspective is there's still this 80 million is counting change received back to spending money, but more than likely only around 5.5 million. Only 5.5 million was actually spent in this block.
And that's them guessing how much actually was transferred to a different wallet.
Yes, exactly.
Right.
Yep. And then the transaction fees, and then the 12.5 Bitcoin block
reward. You could do transaction fees divided by number of transactions. So what, like 10,000 divided by 2,500?
It is 0.0044.
Yeah. So
actually, I'm sorry. I got to do
10,000 divided by
4.4
is just 4, right?
Yeah, 4. Yeah,
it's 4. So $4 a transaction.
Yep.
On average. Yeah. Okay. Cool. But yeah, we can go back to your tool.
No, this is a great way to put it and see it, and then you'll see the rest of the transactions on here. I highly recommend, if you haven't played around with blockchain.info, go there to see the real world, values here, to really wrap your head around what and how much money is being sent in every 10 minutes.
Yeah, so you'll see, the average ones they start with 1, they go to 2. That's your average transaction. 1-to-1, I guess, would be if you didn't. That's you're maxing out your wallet, right? You're spinning. You're not. That's when you hit the max button on your account, because it's not going to have a change address. But
Yep. So it looks like we have another question. So you don't know how much any one person is spending out of their stack of Bitcoins in a single transaction. You can guess.
You can guess.
Yes.
Technically,
you never really know.
No.
Yeah.
No, you don't know. And then some sites will say, it'll say estimate. It'll give you a guess. I think there's a blockchair.com. I can't remember. There's another one Explorer. I just remembered it was pretty cool. I might find that later. But you'll notice that they'll always say estimated value transacted. Because you don't know. But if it's a 1-to-1, then obviously that's how much was sent. But if there's a two outputs, then one of them is most likely a change output. Most likely it's the one of the higher value is yours. It's going back to you because you're just sending a little bit out of your stash.
Yeah, so, and I can show that here. Again, just to reference the inputs. This is the input right here, and then here are the outputs: output 0 and output 1 of a sample transaction. Yeah, as we're saying, we can't tell which one of this is change, which one of this is actually the amount being sent. But you could just assume, So we also have, again, for this standard transaction, this is a transaction pulled on the blockchain earlier today. This is not the Coinbase transaction I was showing earlier. You'll see that this previous transaction hash here, highlighted in blue, is actually filled in. It is pointing to a previous transaction, which is where the input, or the 176 Bitcoin, is coming from, that is then being sent to someone else or back to themselves. Can't really tell. And also the 0.05 Bitcoin is being sent to someone else or back to themselves.
Do you maybe to preface this, what we're looking at, maybe we show them at blockchain.info and do the question mark hex to show them what, this is what it's the transaction hex, the hex dump, and then saying, okay, now this is what this tool is doing. I guess we kind of just jumped into all these numbers. Just pull up a transaction. So this is, while Rob's doing it, any transaction, make sure it says transaction, not address, when you're in blockchain.info.
Yeah. So this is the transaction we just looked at in that tool.
You go up to the URL and just add question mark.
Yep.
Equals format.
Or hex equals, or format equals hex.
And you'll actually get to see what the serialization of the transaction looked like when it was sent through the wires or out of the wallets. This is the information being sent to make a transaction. And then that website we were showing you a second ago is this is going to help us break that down into the understandable chunks.
Yeah, so this is the raw hexadecimal that is the exact same data that is actually right here in front of me.
And that's what's information is being sent. That's all in bytes. And bytes can be converted to bits, and bits is 1 0, and that's what's being sent down, broadcasted when you send out a transaction. And then this is going to help us break it down.
Yep, exactly. Yes. And each color designates a different, a different purpose or a different portion of this transaction, which then can also be mapped back to a little friendlier format such as this, but a much friendlier format is the actual inputs and outputs that you see in this page. So this is all the same. All this data is actually being decoded out of this raw hex dump right here. So this, when I scroll back up here, this derived address, even though you cannot see it, well, there's a QR code, even though you cannot see that, let me go back one. That's cool. You can actually look at the address. So even though this Bitcoin address is right here in this output, it is not actually visible in this raw hex dump. It is actually encoded in one of these, what they call script pub keys, which are actually
that's not in that hex dump.
It's not actually raw in the hex dump. It is actually no. It's
the base 158. Is that what we're looking? Is that the difference?
This is the base 58. Exactly. The hex dump.
So if you copy and paste that and then search that in that last hex dump, you won't find that.
No, because base 58 isn't hex. It's
a hash.
It's another hash. Yeah, I mean it's not a hash, is it? Yeah, it's another hash. It's another hash of it's a hash of the what's it called? Hash 160.
Oh yeah, so it's a RipeMD hash. Yeah. RipeMD SHA-256. Okay, so that you can't look at a hex dump. Which when I say hex dump, that's that thing at blockchain.info. If you add question mark hex equals format.
So this is actually that breaks it down. So the address that we just referenced, the what's called the base 58 address.
Oh, there's a base 58 check right now. Yeah.
Yep, this is the base 58 check address that we use to send and receive money on Bitcoin. It's friendlier to read, easier and error proof. But the actual address in hexadecimal is right here. So if you take this and decode it using base 58 check, you will get or basically reverse base 58, you will get the hex value right here. The hash 160 of that address is right here, and this checksum is then used in this address calculation as well. But yeah, so there is something that the wallet is doing. The wallet is going through and scanning this information and taking this hexadecimal value and basically taking that and running it through some hashes to determine what the actual Bitcoin address is that is being sent to. So that's why it's difficult to see.
You're right.
Yep.
Yeah, because Bitcoin addresses have more than go higher than F, right?
Yeah, exactly. Okay. Yeah, because it's base 58. We got, what is it, X. We've got a J and an H and a Y in there, so that's why.
So that's not like a one way. That's just a conversion, right?
It's just a conversion. Yeah,
it's just a conversion to make it friendlier. I guess you add a 1 too, right?
Yeah, so it's probably not probably not proper to call it hash because it's not. It can be reversed so that it can be decoded.
That makes sense because it condenses it because you got 26 characters compared 20 and little. I don't know. Is case sensitive addresses? Are they case sensitive?
I believe so because each ASCII character is different. This is a different.
256 bits is the address, right? Well, yep. I don't want to digress too much, but yeah, that was a good point. I didn't know that. Okay, thanks, Rob.
So yeah, it's encoded in there, and to get to it, basically, there's going to be. This is just another way to look at it here. There's going to be a few things that are part of this address that we saw on the blockchain reader page. There's going to be the previous transaction hash here highlighted in red. There's going to be the number of the index of the output that we want to reference in this previous transaction.
So the first one.
Yep. In this case, it's the first one since it's all zeros. And then there's going to be how large the unlocking script is. So this is where we want to get into the unlocking scripts and what they are and what they do.
So we got 8B right there. So 8B and so that's going to tell us this
the size.
So the receiver knows, okay, I get an 8B. That is, what is it? What is 8B? What would it say? 200
It's
or
139 bytes.
So it knows the next 139 bytes it gets are going to be part of the unlocking script.
So you see this green here, this dark green. This is 139 bytes of hex, and this hex is then basically an encoding of a script that is to be executed by a node or miner to validate this transaction.
To unlock it.
To unlock
that UTXO. Did we say that? Yeah, it's to unlock which one it's pointing at in the transaction.
Yeah. Yeah, I know we should say the unlocking script is run by the person who is going to be spending that unspent transaction.
Yeah.
So I wouldn't say it's the script that's run by the miner or the node. No, it's actually being run by the wallet software. So when they were going to send that 176 Bitcoin in this transaction, the wallet software had to actually go through here and decode this this unlocking script and execute it to verify and validate and prove that they actually own the key, the private key to those funds or to that address, that wallet address, in order to spend what is actually being referenced in this transaction.
Yeah.
So a lot to unpack there. There's actually
we can talk about but.
There's actually
a lot of ways to go.
Yeah, there's actually a little breakdown here of the unlocking script here. There's a limited language, script language that is called script that is built in to Bitcoin that it actually is used to verify transactions, verify signatures on transactions, and to prove that you are the owner.
So I guess Ethereum's language is Solidity, right? And Bitcoin's language is script. We just never hear script because it's very basic and it's made that way, right?
Exactly. So to show an example of the script language without going too far into it, it is a stack-based language, and there are lots better videos that will go through explaining this. But for example, if you were to say the script was read left to right, if you were to have the values 2 and 3 added to the stack. So I'll just do it this way. So you start with 2. The 2 is pushed to the stack over here. You'll just imagine this is the stack right here. Then you go read to the next value. It's 3. So we'll put the 3 on the stack. So now we have 3 and 2. You'll see us in reverse order. And now we'll read the next value in the script, which is add. So what add does, it actually pops the top 2 items, which are 3 and 2, off the stack, and then adds them together, and then pops the result back onto the stack. So you'll notice 3 and 2 disappear. They're added together, which equals 5, and popped back onto the stack. And then we take, we got constant value 5 is pushed back to the top of the stack. So now we have 5 and 5 on the stack, 2 5s. And then the next part of the script is equal, which says, hey, which validates are the last 2 items on the stack equal. So it pops 5 and 5 off the stack, compares them. If they're equal, it's true. If not, it's false. So
this is what the nodes are doing, right? This is how they're verifying. Well, is the nodes, right? This is the nodes doing this. Yes, right. They're the ones.
Yeah.
Right?
It would
because your wallet can send out whatever it wants, right?
Yeah. Mm-hmm. No, I think you're correct there. Yeah, I definitely think you're correct there because this is how the validation is done. Bitcoin script validation, doing simple math. So this is validating that the script is valid and that the transaction is valid. And now that was just a simple example. You really wouldn't see this on the blockchain. 2 + 3 = 5, and adding 5.
Andreas Antonopoulos, he has 2 good videos on YouTube. Advanced Bitcoin Scripting 1 and 2, part 1 and 2. He gets into this way more. I think it's called, when I say double Dutch last time, it's reverse Polish notation, which is, there's calculator. I think my dad always got on me. He's like, you got to get a calculator like this. You go 2,5 divided by, and you go 2,5 minus, because then you can use the next one, and you save a step. But it's reverse Polish notation where you the operator is put at the end, and your inputs are in the beginning.
Yes.
So instead of 2 plus 3, you do some 2, 3 plus. But
yep. And so a more advanced version of this would just be, the same order of operations here, where we pop a, say, signature onto the stack, and then we go through and then pop a public key onto the stack, and then we continue, and then we duplicate that public key. So now we have a signature, public key, and public key on the stack. We can then move forward, and determine what the hash 160 of that most recent value on the stack would be, which is going to take and run a hash 160 hashing algorithm on the public key, which is the last item on the stack, and then return the result to the stack. So now we have the hash of the public key on the stack. The next value would be, we're going to take the public key hash from the previous transaction and put it on the stack. And then we're going to use equal verify to verify that the public key hash that was calculated previously, and the public key hash of the previous transaction are equal. And once it verifies that they're equal, it will pop them both off the stack if they are true, so that is valid. And now we're left with just the public key and the signature on the stack that we had earlier. And then the last step in the script is to check the signature, which then checks to make sure that the public signature matches the public key. And if it is true, if these are calculated to work with each other, or to validate as true, then the last value on the stack validates to true, and that transaction,
verified.
Yep, that script and that transaction is valid. So that's just it's kind of a difficult way.
Yeah, and it's kind of we're just like, not giving much context, but it's there's those 2 videos I mentioned. It's kind of hard to understand. And I guess this is a pay to public key hash. You get the terms in here.
Yes.
A little much. There's unlocking scripts. There's locking scripts. Unlocking when you want to pull from your wallet, you unlock them, and then you lock them when you send them to the other person, I guess, or their wallet unlocks them because you use their key.
Yes.
But yeah, we'll add the link to that chapter in the book where you can kind of walk through that process. But if anything you know about the stack, that helps. But.
No, it definitely is helpful. We'll put a link to those so you can get a better understanding. So what we're seeing here is like a breakdown of the script that was in that transaction, that 176 Bitcoin transaction I showed earlier. You'll actually see the commands that Bitcoin uses begin with the word op or operation. So earlier you'll see we saw duplicate, which is op dupe, and we saw hash 160, which is op hash 160. Same thing for equal verify and check sig. So this is actually the script or the unlocking script that was used in that transaction of the 176 Bitcoin. And you can actually see the public key that was used in that script to be run to be verified. And there's the full script here, which we won't get into right here. But there's actually a breakdown of how to run the script on this page. Like if I were to click step 2, it would actually show me what would happen if I were to execute part of that script. And step 3, what would happen if I ran duplicate. Step 4 is hash 160, and so on and so forth. So this is kind of a good way to step through the script and actually see what the results are every time you run the script or run a command on the stack.
Yeah. And that's, I don't know, I mean, that might be the most we know about, or talking about the signatures. And
yeah,
we kind of went over this. I think it was episode 2 or 3. I think it was episode 3. We talked about the whole elliptic curve and how the encryption works.
Yes.
But
which is important because that's what's used. That's
what's used, but that's the most difficult part to understand.
Yes. So when you ever see the term signature, that is actually a signature that is generated by using the elliptic curve cryptography or the elliptic curve math that we talked about in the previous couple of episodes.
Yeah.
So it is not only used to create an address, or to create a public key or private key like we discussed in the previous episode. But that elliptic curve math is also used to sign and to verify the actual inputs and outputs of a transaction. And that's important because when you sign an input saying that, hey, I own this Bitcoin, I'm proving it by signing it, that elliptic curve math is then used to verify that you do in fact own that input or that Bitcoin that you're sending. So again, that's where the ECC and all that comes in play to just create a secure location or secure address for your Bitcoin. It's also to provide a proof that you own it and only you own it because you're the only one that owns the private key.
And then I guess after the script takes, we get the lock time. My brother just joined the chat. He said he's going to take a shot every time I say Bitcoin. Bitcoin, Bitcoin,
awesome.
Bitcoin. All right.
Get drunk.
No, boy. Friday nights. Look at my brother's Friday nights. He's out partying. I'm here.
Talking about Bitcoin.
Bitcoin. I love it. Anyways,
awesome.
so yeah, I guess you get the last part of your hex is the last part of the hex dump is the lock time. So we got that the FF78 translated into decimal is what, half a million up there. You see,
right here. 489.
That is number of seconds.
If it's over 500 million, I believe.
Oh, you're right.
Yes. So if it's over a certain value, if this is over 500 million, that is actually the time that this transaction has to wait before it can be included in a block.
So you can delay a transaction, right?
Yes.
So I can say, I want this transaction to happen 3 days in the future.
Yep.
And you can put a lock time in there.
So you would put a lock time of 500 or however many seconds that is into this lock time value encoded in hex. However, if you don't provide a lock time value and you just leave it at 0,
which typically it is, we were told, right?
Typically it is, from what we've seen anyway, and what we're told. But if you do put it as 0, when that transaction is actually included in a block, that lock time becomes a block number. It actually becomes the number that the number of the block that transaction is included in. So in this case, this 176 Bitcoin transaction that was sent, that we showed earlier.
So that gets added to it after the wallet.
This gets added after the wallet, exactly. The wallet sends it with the zeros at the end if there's a lock time. And then once the miner builds the transaction list and builds the block, once they are done, the lock time becomes the block number. So in this case, this is block number 489,727 in the chain. So that's why you'll see if I go back on another transaction within this block, this lock time will likely be the same, 489,727.
So it helps you identify transactions, I'm sure.
Exactly. So that way we can verify, a wallet can verify, hey, I'm looking for a transaction that happened, in this block. Then it could just check for, the lock time, for example, and look for the block number, and then be able to find those transactions that happen there. I mean, that's just one way.
And I think we got, and we can keep going on this, but I think we could take questions from the chat.
Yeah.
There's one question there that I need to look up the answer in.
What do we got here?
So I want to see your face. Where'd you go?
You want to see my face?
Yeah.
I don't want to.
They're just watching the screen and watching me look at the screen.
I'm back.
There we go. Hey.
So someone asked, what if someone rebroadcasts the same transaction? How is that handled? So what I believe is
that address that we have to look up to is obviously not going to. It's going to be moved. So it's going to, it's going to say the input. Okay, it's going to look at this input again. Well, there's no more unspent transaction at that input anymore.
Yeah.
Right.
So if you sent a transaction of 176 Bitcoin in this example, and you referenced an input on the blockchain or an output on the blockchain of 176 Bitcoin that was yours, and you proved it was yours, you spent that, it gets included in a block, it gets confirmed. If someone comes along and tries to replay that transaction, it has to reference the same 176 Bitcoin in the same output of the same transaction, which has already been spent or considered spent at this point in time. So the nodes and the miners will not be able to validate that transaction because the unspent transaction output is no longer unspent. It is now spent.
And so I guess in the case that, let's say you try to send it on the same block, then I'm assuming that I don't know this for a fact, but I'm assuming that the mining would look through and make sure it has unique address, it has unique transactions. So you could maybe send it out twice, but it's in a real short period of time, so it would be in the same block. I don't know, but at some point in the chain, at some point when it's going to the network, I don't know if it's the nodes or the mine, but they're probably going to check for unique transactions.
I would think. I mean, if they're identical, if the transactions two identical transactions are sent with the same inputs, outputs, and they're valid, I would think the first one to be included and the first one to be executed would be the valid one, and the second one would have to be, seen as invalid. But that's a good question.
It wouldn't keep it in the block, I guess. You wouldn't have the same the mine doesn't let it have that transaction twice in the block, right?
So and MTG Cash Cow brought up a good point. He said that so you can't reference the same transaction twice, which is true, because if you think about it, you have to spend all of the input on every transaction. So if you're pointing at a previous transaction that has 176 Bitcoins in it, you have to spend 176 Bitcoins in your transaction. Even if you only want to spend 0.05 Bitcoin, you have to spend the rest of it to yourself as change, for example. So it would no longer be the same transaction, and we can't reference it twice.
And let us know if we're wrong. Please let us know in the comments.
I'm totally right.
I'm not saying wrong. I'm just saying.
No, I'm just joking.
I don't know. True. This, if you guys help us out. There's another good question there. So MTG Cash Cow, man, you're a man. Just keep asking questions. Do the hexadecimals only communicate numbers, or can a miner put in extra information? So I think we got on here on chat page 160, we got flagging, and we didn't really talk about flagging.
No.
It's bit 68 in sequence, and so that's the sequence number. Remember how we talked about it? Says I'm not going to talk about the sequence number after, and it's after the script. It's after the unlocking script. You have like a 4 bytes. I don't know if you can. Maybe we can pull it up later.
Yeah, there's actually not just there. There's the.
That's where you can flag a SegWit or one. Everybody decides 1 means this, 2 means this, 3 means this, 4 means this.
Yes.
Outside talking to each other, and that's where you can put that information to communicate what you're voting for.
And also in the Coinbase transaction, there's actually information that you can encode in there if you were the miner. So if you were to win a block or you were to create a valid block, you can actually encode information in that block. An example is.
I guess it would be the block. I guess the block's very easy to encode information.
Yeah, well, the Coinbase transaction actually has information encoded in it. It actually has
you get the extra nonce right there in the gray.
Exactly. So Coinbase input script, and I think this is where the information is being encoded.
Yeah, it comes from there. So on a regular transaction, that would be your unlocking script. Now for a Coinbase transaction, since you don't have any previous transaction to look up to unlock, you got all this extra space in here to write, I love Roger Ver, Litecoin's awesome, EOS, get a product, you better hurry up, ICO suck, or something. You can write whatever you want.
Let me share my screen here. Yeah.
I love it. No, just went on a little tangent there.
Thank you. No, it's okay. MTG.
Talking about my bad ICOs.
Let me clarify. So I didn't have this on the screen, but if you look here, you see this gray part of the Coinbase transaction, and I guess we didn't make this clear. And this is a common confusion. It was for me. Coinbase has nothing to do with the company Coinbase.
Good point.
This is where Coinbase got their name. It's from likely got their name anyway, is from referring to the Coinbase transaction in a block. but this has nothing to do with the actual company Coinbase. However, this is the transaction that creates Bitcoin and rewards the miner. So when the miner gets the reward, they get to use the Coinbase input script and put whatever they want in there, because really, it, as Bry mentioned,
Quick guy, Bry.
Bry mentioned, there is no previous output or transaction to reference in a Coinbase transaction, because it is creating Bitcoin, not referencing Bitcoin that existed. So they encode information in here. For example, this miner encoded mined by AntPool7. So this was AntPool7 that mined this block. So they'll use that to just encode information in there to identify themselves.
They can or they can't, and yeah. And then so remember the Nonce. So you'll see the very end of there. They have that. I think it's the very end. The one outside of it, is that the Nonce? You go to put your marker. The very edge at the very end.
No, because this is a transaction. The Nonce isn't any transaction.
What's that one hanging out by itself?
This is the Nonce.
Okay, so to mine a block, when you're trying to get that many zeros, we'll talk about mining later. But you can actually use that space after you type what you want. That's going to get Nonce to, or incremented if you will, to find that solution to the block. So they can use that whole space inside there to help create a different Nonce. And that's why you have all that gibberish. I don't know if they probably iterate there and the Nonce, and it's called the extra Nonce in there.
Yeah, so the Nonce is part of the block itself that we'll get into when we talk about mining, but it's just a random number that is generated to change the hex output, or sorry, the hash of the block, to try to achieve a certain hash. And we'll get into that more later, but that is something that can be changed. But I think what it looks like Wasim asked is how much space.
Yeah, so there's 12 and there's 8 of those. So 8 bytes times 12 is, what's that? 8 times 12.
It's math.
It's math.
Math bytes.
Hey, we're engineers, but we don't maintain this one. 8 times 12, 96. So you got
I'm 96. Not doing math.
96 bytes worth of space from extra Nonce, plus your 4 bytes of extra. So 100 bytes of Nonce for.
We want to say Nonce.
I guess not exactly. I just guesstimated 12 of those blocks.
Okay. Or about the gray ones?
96 bytes. Yeah.
And remember the gray ones here. This is actually part of the Coinbase transaction. This is not part of the block, header. The Nonce is in the block header, and then the Coinbase input script is actually part of the first transaction.
Yeah, but they can use that Coinbase input script as part of it's called the extra Nonce.
Oh, is it? Oh, okay.
Yeah, so they can iterate through that Nonce on the header, and they can iterate through because let's say, I don't know. I mean, you got 4
You're right.
bytes of Nonce.
Yeah, there's not enough information there. And that's
probably
what
that might not give you enough to be able to mine all those zeros.
Well, right here.
That is exactly what that garbage is. That is just what happened to be.
Yeah.
The part. So that first part, I don't know. There's no solution. You need to give yourself more space to find an answer. You don't want to take out that whole space and write a whole sentence out, because what if your Nonce doesn't solve the block?
Yeah. That makes sense. Yeah. That makes sense. Cool. Okay, I apologize. Yeah, I didn't realize that, because this may not be enough information to generate the correct hash, so they have to then use more space to generate the valid hash, and then once they're done and they get the valid hash, they can fill in the rest with whatever they want. So not a whole lot of space, as you can see, probably about that much space.
All right, we got another question. So the Nonce is what other miners are trying to decipher to win the next block. If so, would they already know the number? So every miner is going to grab their own set of transactions to put in the block. So it's not like everyone knows, because someone's in Australia, someone's in United States. They're going to get fed transactions. I guess in their mempools are going to be cut off.
Different rates.
So they're going to say, here's my transactions group. I'm going to try to get these in a block. So the Nonce is not obviously going to be, everyone's going to be a different block to add. So the Nonces are not going to be the same. I guess in the rest of your question, was they're trying to decipher to win the next block. If so, would they already know the number?
No, the
What
the
are you saying?
nonce the nonce is truly unique to that miner, and its list of transactions in the block. So it collects transactions, it puts them together in a block, and validates them, and then it starts changing the nonce and playing with it until the entire block, when it's hashed, with including the nonce, comes out
All
with
that
a
information.
hash. Yeah, all the information, including the nonce, will be hashed. And if it's under a certain number, a certain value, then it is valid. But it is only valid after the nonce has probably been changed, millions upon billions of
Yeah.
times.
And take one transaction out of that whole block, that nonce has nothing to do. They're going to mine a totally different block.
Yeah.
And there's no patterns. There's no relationships between. And that's the point of the hash. It's totally you hash the word hello, you hash the word hello with a capital H, and one's lowercase. Totally different hash outputs. Which
Yep, you can see
so one
an example
transaction out of
here.
the whole block is totally going to change it.
You can see a quick example here, and we'll cover this more in the mining episode. This is a mining simulator. So imagine the nonce is right here, and it's literally just incrementing the number by 1 at a much, much, much slower pace than an actual miner would. But as this number changes, you'll notice that the headers are actually changing. And then the Coinbase transaction, I don't believe is changing yet, but the computed block hash. So every time that nonce is incremented, the computed block hash, the hash of the entire block and its transactions, is changing as well. But the target block hash is to have this many zeros in the beginning of it, which is the best way to put it is you're trying to change the nonce, run it through a hashing algorithm to truly randomly, get a value that is less than this value.
Yeah, that's just what Satoshi decided, right? That's just
exactly
how I'm going to say they verified the block. It's just the number's got to be, and as the difficulty grows, you got to be less than that number and more or less, and So yeah, we'll talk about. I don't want to talk too much about mining because that's gonna be a fun episode. But
exactly. But this is just the best way to look at it, is that you see that there's rarely ever a double zero in the beginning, and even when there isn't a double zero in the second, third, fourth, fifth, sixth, seventh, eighth, and ninth place. It takes an immense amount of computing power to randomly
trillion. So a trillion. When my A67 is 4.6 trillion per second. So
there you go.
Take these guys with peta. We're exabyte. We're at huge. I mean, they cost tens of thousands of dollars worth of electricity just to generate something that so it's incredible the amount of guessing to get the block right. It's proof of work. You're proving your work.
Yep, and I think Wasim has a good question that we may not be able to answer just yet, but so if they remove the space per transaction that the miners are allowed to add info to, then we can fit more transactions in a block, kind of like SegWit. Why didn't they do that? Well, I mean, honestly, my guess is that the Coinbase transaction is just one transaction, and it only contains so much space for room for a miner to include extra information.
Yeah, that's not going to do anything to help it
Whereas,
that many bytes. I guess. I want to cut you off.
Yeah, I mean, a block is roughly a megabyte, and this text right here is probably just going to be a couple of bytes saved. So, if this information was included in every transaction in a block, for sure, I think that would have been gone, a long time ago to save space. But this is just the Coinbase transaction, which is only one per block. So it really doesn't save much space.
So you're talking about 250 divided by 1,000,000%, whatever that
exactly.
is. Of saving now, and you also need that space to be able to mine. So, other than that, if you guys got any more questions, thanks for sticking us with the three people.
Yeah,
you guys are the best. This is not the stuff that people want to talk about. Yep. This is the important stuff that's going to get you a job. Because now a lot of people know that's why we're trying to do this too. I'm not going to lie.
Yeah. This is
the stuff that's going to be the most valuable to learn if this thing really takes off like we think it is. So
yeah, and all this applies to other almost all of this applies to other altcoins and other blockchains like Ethereum. It just varies. Some of the technologies slightly different. They use maybe different algorithms, different, what's it called? Different hashing algorithms, different security algorithms. However, the blockchain, and how they're constructed and how the rules that Bitcoin follows, a lot of the altcoins out there initially started following those rules or still may be built upon the actual Bitcoin code. So learning this is also very helpful in understanding how Ethereum and Litecoin and many other coins out there work. And
it's gonna be nice once we get through this book. I think we'll be excited to talk about current events a little bit. Just kind of bring it home. If you guys, any of you watched all the episodes in a row, I'll send you some money. So you can prove to me somehow.
Yeah, and it looks like Lokesh had a question earlier. Many users have thousands of unspent transaction outputs under their account. Why not wallets? Why do not wallets do a transaction once a week or so, or a month, automatically pointing to the same wallet worth the sum of all unspent transaction outputs?
I think they do that, but a wallet's not going to. It's going to cost a wallet money to do that. And I think sorry, exchanges do that.
Yeah,
I think exchanges did to consolidate the money into one address.
Yeah. So if you think about it, if you think about this, say you have thousands of unspent transaction outputs, and your wallet just automatically takes those, puts them in one transaction, and sends them to one address to consolidate them, that will incur quite a bit of fees. We were looking at a transaction that had just like a couple of inputs.
How much was the fee?
The fee was what, $31?
No, there was 80. There was a what, $120?
There was
$120 transaction with a $60 fee.
Yeah, and that's you could get that if
you're just taking up that much real estate of the block,
Yeah, so. Exactly. So it's all about how many bytes your transaction takes up, and that increases with the number of inputs you include and the number
outputs. Yeah.
So if you have 1,000 inputs, you're gonna have an
You're pay for it.
So that's why we wouldn't want to do that weekly, or
so
if at all.
Always send money to a new address, and always, don't send money to the same address or collect money to the same address, right?
Yeah, and the beauty of wallets are they keep track of this all for you. The thousands, if not tens of thousands or millions of unspent transaction outputs, it doesn't matter if they're out there. It really doesn't matter to us. Because the wallets are designed to keep track of all those addresses and keys, and as long as you back up your what's it called, mnemonic seed, or mnemonic, then you really have nothing to worry about, because even if your wallet software disappears or crashes or goes extinct, you can import that seed into another wallet software, which can then scan all those addresses, find all those unspent transactions for you, and add them all up into one balance, and abstract it into one balance for you. But I would
other
say,
than that, you guys, hope we didn't bore you to tears.
Yeah.
But if any other questions, I think we're good. Oh wait, does anybody say anything? I don't think so.
No,
So I guess our next episode is on advanced transactions.
Yes.
So I think I really wanted to have the goal of, we're going to get in the test net, and we're going to try to build. We're going to try to take each of those chunks, copy and paste, and we're going to see if we can send testnet money. So maybe one of you guys can give us an address on the testnet, and we'll send you some testnet coins.
Yeah,
so,
and hopefully
we'll try to do that next time.
Yep, we'll definitely cover transactions more and get a real world example to help you wrap your head around it. And let's see here. It looks like Lokesh said his concern is not about wallets. Bitcoin database size is increasing in gigabytes per year. And I think that is definitely a concern, but I think that'd be a topic for another time. But in my personal
opinion, the wallets don't obviously they're what, single point view. The wallets they're not full nodes, but so they don't have all to carry all that in the whole block. And I think they're talking about you can only have to know like the last 50 gigabytes in the future nodes of a block. It's not like you need to have they're working on it, because it's going to get big.
Yeah,
So,
it's going to get big, but 150 gigabytes for 9 years worth of transaction data, I don't think that's really anything we need to be concerned about just yet. With the size of storage, increasing, a 40 terabyte drive being possible in the near future. So I don't really have too much to worry about this time, but obviously.
But you do need to get it out to all the users. You need to be
fundamentals.
But so I think they are working on different ways to have a half node or I'm not.
Yeah,
pruned. Wrong, but there's a way of pruning it. So,
yep.
Other than that, then.
Yeah, well, we'll learn more about that and hopefully discuss that.
You guys can join open source and solve that problem, right?
Yeah, exactly. That's the whole point. We don't have all the answers, but thank you for all your questions, guys, and joining us. And we'll see you guys next week when we cover advanced transactions. Okay.
All right. Later, guys.
All right. Thank you. Later.